All right, we're going to begin something totally new with polynomials, and it's called factoring polynomials. All right, and I'll explain what that means in a minute. But in this lesson, we're going to talk about a specific type of factoring, and it deals with what are called greatest common factors. And we'll abbreviate that phrase often, and we'll just say GCF for greatest common factor. Okay. Now, first of all, let's just talk about what this idea of factoring is. Okay, and I'm leave a little bit of space if you write this. But the idea of factoring is let's just say I told you to factor six. Okay, the number six. All right. You'd probably say that six is equal to two times three. Okay, you could also say it's one times six, but usually we try to find other factors as well. So what did I do here? I took the number six and I wrote it as a product. And see, these are simpler numbers. These are actually prime numbers right here. So that's the idea of what factoring is. It's taking something, and if possible, it's not always possible, but you're going to write it as the product of two simpler things. Okay? And so now we're going to do this with polynomials, but I'll just say writing an expression as a product. So remember the word product means multiply, so we can see that here. Here's that product. Uh, Writing it as a product of simpler expressions. Okay, and this isn't always possible, by the way, too. Okay, and so, um, but that's the idea of what factoring is. Okay, and then, like I say, and then there's different ways to factor with polynomials. The most basic way and the most common way is to factor out what are called greatest common factors. Okay, or a single polynomial will have at most one greatest common factor. All right, so um, now what's going to happen here with factoring GCS? Okay, so the bigger picture of what factoring is writing an expression as a product of simpler things. Now we're talking about given a polynomial, we'll just factor out, if possible, what's called its GCF or greatest common factor. Okay, and what it basically does is it reverses distributing. Okay, like that. And what ends up happening in math, this is going to seem kind of silly at first why we would want to go backwards, but more often than not in math, we actually want to factor an expression to get it in a simpler form, and it allows us to solve a lot of uh, more general application problems. All right, and so, but it does reverse distributing. So the way, whenever we write the general principle for distributing, we usually write that. Some quantity times a sum. Remember the idea here is that we usually multiply that through, right? Like that. And so we say that it's equal to A times B plus A times C. Okay? Now make sure you realize we're saying that two things are equal. Whenever we say two things are equal, we're used to reading left to right. So we just read this way. We think that we always have to distribute a parenthesis. Okay? But whenever two things are equal, you can read from right to left too. Our just brains have trouble with it because we're so used to reading left to right. But what this is saying is that if I have this kind of quantity where you're multiplying, you have a product, you have another product with a plus, and but one part of the product is the same in both sides. What this property is saying that you can bring it out front. All right. And so I'm going to go ahead, since our brains have so much trouble with that, I'm going to just say, I'm going to write the property the other way around. Okay, and this is the distribution or the factoring form of the distributive law. Okay, so again, the idea is you have two products. Okay, so remember, a product is a multiply. So here's one product, here's another product, and we're adding in between them. Okay, but the key thing is about these two products is they have a factor that's the same or common to them. Okay, and so then what the distributive property says is that I can take that common factor out front and leave the other pieces inside. Now, another important thing about this, if you remember, distribution also applies to subtracting. So I could be subtracting instead. If you're not used to that symbol, that just means that you either adding or subtracting, adding so then we could write this distributive property the same way. Okay, and so all that strange notation is saying is that if there's an add in between them, the add stays in the middle. If there's a subtraction between them, it stays as a subtraction in the middle. Okay, and so that all this is it's the distributive property written in terms of factoring. All right, so enough explanation. Let's see how we can make this work for us. All right, so let's just look at two very basic examples, okay? And remember, and just remember, we're going to be using this property of reversing the distributive property, okay? Once we get comfortable, we'll learn another way to do this, but this will just help us to get started to see how that property works. Okay, so notice that in this first example, we have 2x. So remember, that means 2 times x, okay? And so this is like my a and my b up here, okay? That you can think about that 2 as being the a and the x as being the b, all right? Like that. And so the idea is that we can also write 6 as 2 times something, okay? And so I can think about this as being 2x plus, how do I factor 6 in terms of 2? It's 2 times 3, like that, okay? So now where we can really see that form, like I said, this is like that a times b. But notice the first part of the second term also has the same thing in it. And that's the reason we use that same letter A. And then we can think about that 3 as being the C. So what the distributive property in reverse allows us to do is notice that A comes out front. Okay, so that means that 2 would come out front. All right, like that. And then in parentheses, I'm just left with the other parts, like that. And so this is called the factored form. All right. And like I say, it's very basic but very important property in math. Okay. Before a little bit more explanation too, let's go ahead and do this other one. The main purpose of the other one is to try to explain what I was talking about, this plus or minus. All that means is it doesn't matter if you have a plus or minus in between the two terms. It still works the same way. Okay. And so in this one, notice I have the 5 times x. And so, and notice that 5 also goes into 20. And so I can write this as 5x minus 5 times 4. And just to help you connect it with that property up above, here we have something times something else. But then over in the second term, I have the same first part. So I would relabel it A again, and then times some number C. And so what that distributive property says is that the common factor is what it's called, comes out front, and then the other parts get left behind. Now, one other nice thing about factoring is that you can always check factoring. What's the idea here? This is 2 times some quantity in parentheses. So I should be able to distribute this and get back to where I started. Now, these examples are so basic it might seem kind of silly, but you can always check factorizations by just factorizations of polynomials just by redistributing. And so here I'd get 2x plus 2 times 3 is 6. So that does check. Make sure you realize that's the check, but here's the answer to the problem. Okay, same thing here. If I wanted to check this one, I would start with what I think is the answer and then distribute it. And I would get back to my 5x minus 20, which is what we started with. So a nice thing to realize about factorizations. One other thing too to point out is with some vocabulary. Notice that we factored out the two. I keep saying factored out right there. So those two things right there in each one of the problems, we call that the common factor, a common factor. Okay. And well, I'll have to explain this in a moment, but it's actually the biggest common factor that we could have taken out. And so in this case, this is also what's called the greatest common factor, which we'll just abbreviate GCF. Now let's look at two more examples that might kind of bend your brain at first. But here, think about this. We can think about this as being x times x, the x squared. Okay, and see, notice here I have 4 times x. And if you really want it to look like that distributive property, you don't have to. But you can, remember, it doesn't matter what order we multiply things. we can think about this as being x plus 4. And so to really write this one out, you can think about this as being x plus times x plus x times 4. Okay, and so the reason I'm pointing that out is notice this first part I could write it as a product, a general product, a times b. But again, the first part of this term is the same as the first part of this term, and so I can think about this as being an a times a c. Okay, so using that distributive property, what are we seeing here? That we have a common factor here of x. Okay, like that. And so whenever I have a common factor, I can take it out front and then multiply by what's left. Now, it might help you too. Again, I'm going to show you another way to do this in a moment, but it might help you since you took, especially with this x times x part, you might want to cross that out to see what's left. All right, and so there's one x left, and then plus there's a 4 left right there. And then think about checking that one. We have x times x plus 4. If I go and distribute, okay, I'm going to get x times x, which is x squared, and then plus x times 4, or 4x. So that does check. We know our answer is correct. And again, I know these checks are basic, but we're going to see more complicated problems in just a little bit. And anytime something's easy to check, you want to take advantage. Okay, so part of this this third example here is just to show you that a variable can be a common factor. All right, and what we'll see is often a common, the greatest common factor will be a combination of a number and part of a variable. Now, this one's a little bit more complicated, and you got to be careful. There is an x that's common to both of these, and you could factor out an x. What we're going to see, though, it's not the greatest common factor. Okay, and so let's just really write this one out explicitly, and so that you can see. If you think about x cubed, that's x times x, right? Like that, and then minus 5x squared, like that, that's 5 times x. So what all do they have in common? Okay, yes, they do have an x in common, those two, but notice that they actually have two x's in common, like that. Okay, and so when in terms of terminology that we'll use here, it's not just if I wanted just to find a common factor, okay, I could say that that's equal to x. But the biggest common factor, which we refer to as the greatest common factor, is x squared because each one of those have an x squared in them, or two x's multiplied. Okay, and so now what I can do is I can think about writing the first part as x squared. Okay, so that's these two together. So then what's left is this single x right here. So it's x squared times x, and then minus x squared. All that's left, if I isolate out the x squared from the second one, is the 5. Okay, so it's x squared times 5. All right, and so here's my common factor right here, that x squared. So I can take it out front. All right, since I took out the x squared, I'm going to cross it out to help me see what's left. And so what's left in the parentheses? X minus 5. Okay, and we can check that. We just pretend like we started with the answer and we're going back to multiplying. All right, and so I want to distribute that x squared there, and I would get x squared times x minus x squared times 5. X squared times x, remember we add exponents, so we would get x to the third, and then minus, we usually write the coefficient out front, and so we have that. So this does check. Now, again, if you're confused about why that checks, this is what it checks too, and see, notice that's what I started with in my problem. Okay, so we know that that is the correct factorization. Okay, yeah, not only can the variable be a common factor, but powers of the variable can be the common factor. Okay, and so next we want to talk about how to actually find a GCF. One quick thing before we move on to a general rule that I need to show you. Kind of ties in with that last example. But say I have 4x minus 8. Okay, so you might look at these two numbers and say, well, 2 goes into each one of them. So, and you're correct that there is a common factor of 2. Okay, but is that the biggest number that goes into both of those? And if you look at it carefully, 4 actually divides into both of those. So yes, 2 is a common factor, but it's not the largest or the greatest common factor. The greatest common factor is equal to 4. Okay, like that. And you can convince yourself. I just wanted to point that out before I write a rule about GCS. Whenever you go and factor that, you'll end up with 4 times x minus 2. You might want to pause and see if you're starting to get it, how I got that answer. Okay, so if we look back at these examples 4 and 5, okay, so on example 4, uh, we had x to the third minus 5x squared, and we got that the GCF was equal to x squared. Okay, and then if we look at an example 5, uh, then we had 4x minus 8, and the GCF wasn't 2, but it was equal to 4. Okay, to do more general factoring of greatest common factors, what will happen is often the GCF won't just be a power of x or just a number. It'll be a combination of a number and a variable. Okay, and so we can actually get to a rule for GCF. Okay, like that. And what it is it's some number times some power of the variable. Now, again, sometimes one of these won't appear, just like with these two examples right here. Okay, sometimes it is just the power of the variable. Sometimes it is just a number. Sometimes there's no GCF. In those cases, we might say that it's 1, but we'll talk about that in a minute. Okay, but just to be able to get right something. So if you notice here, for the number part, okay, let's think about example 5 right there. Okay, why was 2 not the GCF? Because there was a larger number that divided into both of these numbers. Okay, now is there a number that's even larger than 4 that divides into both of these? No, because 4 is equal to 4, right? Like that. So what we'll say here is that it's the largest number that divides into all the coefficients. Okay, and that all is important right there. Okay, like that. We'll see some examples of what I'm getting at there. And then times, if we look back at example 4, okay, uh, so it's going to be the variable. But notice that we get exponents. Okay, and so with the so let's look back at example 4 right there. We had x to the third and x squared, but which power did we factor out? The smallest power, okay? And so it's going to be the variable with the smallest exponent. Now this one's a little bit of a caveat, okay? And we got to be careful with this. The only way a GCF ends up being having the variable in it is the variable has to appear in every term. Okay, so it's the variable with the smallest exponent if the variable is in every term. Okay, and I'll kind of explain that in a minute too once we see an example. But we can take this as a rule for finding a GCF. Okay, like that. Now, be aware, sometimes this is 1. Okay, the largest number that divides into all the coefficients. Also, whenever the variable's not in a term, you can think about it as being 1, which is x to the 0. And all that means, don't overthink that, all that means is it'll be a case like this where the GCF is just a number. Okay, so don't overthink that, and let's just get to some examples to start trying to lay that out. But I want to show you one other shortcut too, because think back to example 4. That's a little confusing whenever you have x cubed minus 5x squared. to think about factoring this first part as x squared times x, and then thinking about rewriting that second part as x squared times 5. So I want to show you a little shortcut that we can do first. And I wouldn't even necessarily call it a shortcut, but it's a way to make figuring out what gets left inside the parentheses whenever we take out that GCF. So that's all I'm really trying to get at. Well, let me do this. I can do both things at once. Okay. So say I have something like 4x to the third, and then plus 2x to the second. Okay, and I want to try to factor that. Okay, like that. So let's just practice with that rule too. Okay, and so let's find that GCF first. Okay, and so it's the largest number that divides into all the coefficients. That, and then times the smallest value, the smallest exponent in the variable. Okay, like that. All right, and that again is if the variable's in every term. But notice that the variable is in every term. Okay, and so to get my GCF, all right, let's think about this part first, the part with the variable. What's the smallest exponent in the variable term? Well, that would be, here we have a third power, and here we have a second power. So it would be x to the second power. Okay, and now for this part right here, we need the largest number that divides into all the coefficients. So let's look at our coefficients. We have a 4 here and a 2 here. So what's the largest number that divides into both 2 and 4? And that would be 2. Okay, so our GCF here is equal to 2x squared. All right. So now we're ready to factor. What I'm going to do in this first one is I'm going to do it like I've been doing the previous ones. Okay. And then I'm going to show you the shortcut or the other way to do it. I'll quit calling it a shortcut. Okay. So what we want to do is we want to factor each one of these parts in terms of our GCF. Okay. And actually the second part is easier, all right, to look at is that here we're going to have our GCF, but our GCF is the same as what's in my second term. So what could I multiply that by? I could multiply it by 1. Doesn't change its value. Okay. And then in my first part, my GCF is 2x squared. Okay, like that. And then how could I end up getting 4x to the third out of that? It's pretty obvious I'd have to multiply that 2 times a 2. And then to get x to the third, I would have to multiply it by an x. Okay, so now right here is my common factor. So by that distributive property, I can take it out front. And so I have 2x squared out front. All right, once I've taken it out front, I can cross those out. And so what's left behind? 2x plus 1. Okay, so you can do problems this way. If that's making sense to you, feel free to do them that way. It just requires a little bit of sophistication and really understanding those exponent laws and how to factor down individual parts. Okay, so let me show you another way you can do this. Okay, and again, we always find the GCF. Okay, and so you find the GCF, which would be 2x squared. Now what you can do is you take your original problem, 4x to the third plus 2x squared, all right, and then write the GCF out front with the parentheses. And this alternate method is just, to me, a cleaner way to figure out what gets left inside the parentheses. But very important to write the GCF out in front with your parentheses. Students, whenever they use this method, they'll often forget to write this, and then the problem won't check. Okay, so now what you do is you go back to right here. And the thing is, it's a little deeper, a little deep to explain, but factoring and dividing are basically the same thing. And so whenever I factor individual parts, I'm really dividing. So long story short, what I can do is I can come back over here to my original and write each part, each one of them over the GCF. Okay, like that. And so just remember that's dividing, what did our last video talk about? Dividing monomials. And see, this is just dividing two monomials right here. Okay, and so all I have to do is divide those. So in my first one, remember what I do is I divide or reduce the coefficients. So I have 4 divided by 2, and so 4 divided by 2 is 2. And then I have x squared over, or x to the third over x squared. Remember, what do? I subtract exponents. And so I have x to the 3 minus 2, and that would be x to the first. Okay, but remember, we usually don't write the first power, and so we would just write 2x. Okay, then we can say plus, all right, and then what do we have here? We have 2x squared divided by 2x squared. Something divided by itself, remember, is 1. So we get that 2x plus 1 that we already knew from the other method. But that's the way I like to do these problems with GCFs is I'll find the GCF and then I'll write it out in front of the parentheses and then realize to get what's left in the parentheses, I go back over here and I divide by that GCF. Okay, so let's just practice a bunch of examples. We're going to start pretty basic here. Okay, so the first thing we want to do in this first example is find the GCF. All right, and so my GCF here. So first of all, we need to get the number part. And so the number part is the largest number that divides into all the coefficients. Okay, and so let's look at this. We have 6 and 4. What's the largest number that divides both of those? And hopefully you see that that would be 2. Okay. Now, we have our variable x. It's in every term. Okay. And so we do have x. And then what's the smallest power that it appears to? It's to the fifth power, like that. And so our GCF is 2x to the fifth. We've got to be really careful too. Whenever you say that the variable is part of your GCF, like that, it has to appear in every term. And I'll show you an example of that in a minute. I just wanted to get this basic rule down first. All right. So now once we're confident we actually have the GCF, what I would do is I would rewrite the problem and then say equals and then write your GCF with parentheses. And the idea of this dividing is to figure out what gets left within the parentheses or inside the parentheses. So now I just pretend like I have two problems from our last section, and we're just going to divide each term by 2x to the fifth, like that. And each one of these will be a monomial divided by a monomial. Okay, and so to actually get this now, first we do 2x to or 6x to the eighth divided by 2x to the fifth, and so 6 divided by 2 is 3, and then I subtract the exponents. 8 minus 3, 8 minus 5 is 3 as well. So the first part in the parentheses is 3x to the third. Okay, and now I just come to this second one here, and I do 4x to the fifth minus 2x to the fifth. Okay, one thing I forgot to point out too is notice that this problem had a subtraction in the middle, so that'll stay there. All right, like that. Okay, and now we go to that second part, and we do 4x to the fifth divided by 2x to the fifth. So we have 4 over 4 divided by 2, that's 2, and then I subtract my exponents, and I get x to the 5 minus 5 is 0. Just remember, x to the 0 is 1, so this is 2 times 1, or 2, all right? And so all that's left on the right part is minus 2, like that. So there's our answer. And again, remember, you can always check, all right? So try to get in that habit. It's a very nice thing about factoring. And in higher level classes, I always have to remind students to check their factoring because it's so easy to make a silly mistake. And like I say, we use factoring to solve a lot of more advanced problems in math. So if you miss factor, then everything goes goes astray from there. So anyway, so we can always check our factorizations by multiplying. So in this case, whenever we factor out a GCF, we can distribute. And so we have 2x to the fifth minus 3x to the third minus 2x to the fifth times 2. So now whenever we're multiplying, we multiply the coefficients and we add the exponents. And then minus, over on the right, all I have is 2 times 4, x to the fifth. And just try to look and make sure what you're saying it should be is what you started with that. And this one does check. Now you can see it gets a little, there's a lot going on here. So make sure to remember what your answer is here. It's right there. Okay, so now what I wanted to point out with the second example is the concept, all the examples we've looked at only have two terms, but this concept carries over to more than two terms, all right? And so this polynomial in this second example has three terms, but everything works the same. The only thing is to get my GCF here, my net, whatever, if I get the number part of it needs to divide in all of the coefficients. So I need a number that divides into 10 and 15 and 5. Okay, like that. And there is a number, it's 5, right? And that is the largest number that divides into all of them. So the number part is 5. Now, if the variable is going to be in our GCF, it needs to appear in every term. See, notice that there's a y in every term, like that. So y will be part of the GCF, and what is the smallest power it appears to? The second power. Okay, so our GCF is 5y to the second. All right, so just following my advice, hopefully, but if you like it the other way, you're welcome to do it that way. All right, like that. And so I just rewrite the problem, and then I say equals the GCF times parentheses, and then we're going to figure out what goes inside of these parentheses here. All right, and remember the way we do that, we go back over here and we divide everything by the GCF. All right, like that. And so here on our first one, we do 10 divided by 5, which is 2, and then I subtract exponents. 4 minus 2 is 2, like that. And then and then I have plus, then I do 15 divided by 5 is 3. I subtract the exponents, I get y to the 3 minus 2, which is 1, but we don't write that exponent, okay? And then here we have minus, we have 5 divided by 5, which is 1, and then y squared divided by, or yeah, y squared divided by y squared is y to the 0 when I subtract the exponent. So this whole thing becomes 1. And again, too, if you're keeping an eye out, anything divided by itself is 1. So if you just happen to notice that you have the same thing divided by itself, you could just write it as 1. But anyway, what is that telling me? That's telling me what's left in the parentheses. I have 2y squared plus 3y minus 1. Okay, like that. And so this looks like it's the answer. Again, I'd advise you to check though. And so I get 5y squared times 2y squared plus 3y minus 1. And if I go and distribute that, then what do I have? I have 5 times 2, which is 10. Y squared times y squared, I add the exponents, I get y to the fourth. And then 5 times 3 is 15, so plus 15. And then y squared times y to the first, I add the exponents and I get 3. And then minus 5y squared times 1, anything times 1 is itself, like that. And so then I look at this and I make sure it's the same as what I started out with. I do agree. And so now I know I have the correct answer. And I'll circle it. Okay, so let's look at some more examples. These ones have kind of anomalies in a sense, but they're actually more basic than what we've been doing. All right, so let's look at problem 3. We have 14b squared minus 21. And so we want to find the GCF. Okay, so the first part of the GCF is the largest number that divides all the coefficients. So I have a 14 and a 21. What's the largest number that goes into both 14 and 21? 7. Okay, like that. Now, for the variable part is the smallest power that appears. So you might think it's b squared, but it's only if the variable appears in every term. And see, there's not a b in this one right here. So this actually is just the GCF. So if the variable is not in every term, the GCF doesn't have the variable. I will explain another way you can look at it if you really want to is remember I can think about this as being 21 times b to the 0, like that. And so the smallest power that appears is b to the 0, but b to the 0 is 1, so I get 7 times 1, which is equal to 7. All right. To me, it's just easier to think in terms of if the variable's not in every term, then the variable's not part of the GCF. Okay, so here our GCF is just a number. It's the number 7. So as of before, we rewrite the problem, and then we say equals, and we put the GCF with parentheses, and then we come back over here and divide each thing by our GCF. All right, there we're just dividing numbers. So 14 divided by 7 is 2. The b squared doesn't change. And then minus 21 divided by 7 is 3. And so that would be the answer. And again, you could check it. Hopefully you'll get to the point where you can just check in your head. Just be careful whenever you do that. But, it's just, sorry, I'm thinking and talking at the same time. But it's easy whenever you just look to convince yourself that something's correct. Uh, so anyway, we have 7 times 2, which is 14, and then b squared when I distribute, and then minus 7 times 3 is 21, and that's where the problem started out at. So we know we're correct there. All right, now in this next one, um, let's see what we can do. Okay, and so with this next one, we start with our GCF. Okay, and so we're looking for the largest number that divides all our coefficients. So that'd be 5, 3, and 7. The thing is, 5, 3, and 7 are all prime. Now, that's not the reason for this. You could have non-prime numbers, but there's not really a number that goes into all of those. There is always a number that divides into numbers, and that's 1. So you can think about it as being 1. All right, now notice that the variable is a, and it does appear in every term. So then what's the smallest power of that variable? A squared. And so we would just say that the GCF is a squared here. So in this problem, the GCF is just a variable part. It doesn't have a number in it. Okay? And so now to get started with the factoring, we have 5a to the fifth plus 3a to the third minus 7a to the second. Then I write the GCF with parentheses, and then I can come back over here and divide everything by the GCF. Look at that. All right, and so now we're just dividing a bunch of monomials. And so here we have 5a to the fifth divided by a squared. There's no number to divide, and then I subtract the exponents. Okay, and then I have 3, and then I have a squared minus a to the third minus a squared. I subtract the exponents, I get a to the first, and then I have minus 7. A squared divided by a squared is just 1, or a to the 0. All right, like that. And so as far as my answer goes, what's in the parentheses is 5a to the third plus 3a minus 7. All right, and that's the answer right there. Okay, and again, you could check that. I'm just trying to save time. I know this video is getting long. All right, and so now let's look at the example number 5. All right, and so for as far as the GCF goes, uh, I'm looking first for the number. I'm looking for the largest number that divides into 7 and 5. And the only number that divides into both 7 and 5 is 1. Okay? And then for the variable part, notice here I have an x squared, but there's no variable in the second part, like that. All right? And so um, so there's no variable part, or you could think about it as being x to the 0. Long story short, the GCF is just 1. Okay? Whenever the GCF is 1, what that means is you can't factor out a GCF. Okay? And so since our GCF is equal to 1, there's no factorization, at least by GCFs. Now we'll see examples later. Uh, So that's probably the best way to answer that problem right there. All right. So just because something doesn't have a GCF doesn't mean it doesn't factor in the bigger picture, though. So you got to be careful if by saying that there's no way to factor it. So let's just say that there's no factorization by the GCF. All right. So we have enough to get you started with factoring GCFs, but there is one kind of technical thing that happens sometimes is whenever we have a polynomial and the first term is negative, we often factor out the negative. All right, so I would just want to show you how we can do that. All right, so let's look at this basic example right here. And so if we think about getting the GCF just by our normal rule right here, leave a little bit of space out front, but first we look for the number, the largest number that goes into all the coefficients. And so we have a 2 and an 8. So hopefully you see that a 2 is the largest number that divides into both of them. Okay, and then notice there's no variable term, or there's no variable in the second term. So typically you might say that our GCF is just 2, but since our polynomial begins with a negative, we want to factor out that negative part as well. So we would actually say that our GCF is negative 2. All right, and now from there, everything proceeds the way we've been doing it. So rewrite the problem, write the GCF out front with parentheses, and then to figure out what gets left inside, we just divide each term by negative 2. Okay, like that. And so here we have negative 2 divided by negative 2. So that's two negatives. It makes a positive. And so we get positive 1x squared. All right. And then plus, now here we have 8 divided by negative 2. That's a positive divided by a negative. So our answer is going to come out negative 4, like that. And then notice that I have this plus and minus right here that I would rewrite as just a minus. And so, and then remember, we don't write a coefficient out front, so we would say x squared minus 4. And then again, remember, that's telling you what's inside the parentheses. And so we have negative 2 times x squared minus 4. Okay. Now, factoring out negatives works just like multiplying in with negatives. You can check the signs. Is notice that in my original problem, I started with a minus and then a plus. After I factored out a negative, inside my parentheses, I have a plus and a minus. So the signs reverse. That's a way you can at least check the signs. But again, hopefully you'll get into the habit of checking anyway, so you can catch that if you do make a mistake. And so if I go and distribute that negative 2, I have negative 2x squared, and then I have negative 2 times essentially negative 4, so I'm multiplying two negatives. So I get plus 8, like that, and that's the problem that we started with, so that checks. All right, one other example here. I think you'll have enough to get going on. Let's say I had something like negative x squared plus 3x minus 8. Okay, like that. And I wanted to find its GCF. All right, and so we go and start trying to find the GCF. And remember, it's the largest number that divides all the coefficients. And again, too, if you're having trouble remembering, remember since there's not a coefficient here, it's really 1. All right, and so what's the largest number that goes into 1, 3, and 8? That would just be 1. All right. And then also notice for the variable part, this last part doesn't have the variable in it. Okay. And so there's no variable part of the GCF. But what's the deal here? Why am I saying there will still be a GCF? This polynomial begins with a negative. So we'll actually um, factor out a negative 1. Okay, so anytime a polynomial leads with a negative and we're factoring, now we're not always factoring though, but if we are factoring, then you'll factor out at least a negative 1. Sometimes there's more to the GCF. There could be a variable part too. But all this deals with on this slide is anytime a polynomial begins with a negative and we're factoring, we want to factor out that negative. Okay, so remember how we get started. We can rewrite the problem if it helps you write that 1 in front of the x squared, like that. And so we're factoring out a negative 1, like that. And so remember how we do this. We divide each part by our GCF, like that. Okay. And so notice right here, I have negative 1 divided by negative 1. That makes positive 1. And so I could say I have 1x squared if I wanted to. Oh, here, let me do what I was doing before. So I could say I have 1x squared. All right. And then here in this second part, I have a positive and a negative. So that tells me it's going to come out as a minus. And then I'm just dividing by 1, so I get 3x. And then here I have two negatives, so they make a positive. 8 divided by 1 is 8. Just remember, we usually don't write that 1 out in front. And so we could say that this is inside the parentheses is x squared minus 3x plus 8. Okay, like that. And then again, notice at least the sign check. We started with minus, plus, minus. We look inside the parentheses, it's just the opposite, plus, minus, plus. So at least we know we got the signs right. One other thing too, it's fine to leave your answer like this, at least in my opinion. But remember, we often don't write 1 as a coefficient. So some people, I'm just warning you about what you might see. I don't mind if you leave that negative 1 out front, but some people will rewrite this as negative parentheses x squared minus 3x plus 8. Okay, well, I think that's going to be enough to get you going, and I hope that helps. And let me know if you have questions.